Hello friends, today we are going to talk about the another problem in the quantum mechanics and is well known as infinite square wave potential. Supposedly we have the potential energy such that it is a zero within the given boundary region between the 0 to a. So within this region the potential is 0, and outside that there is a infinite potential. Okay, so there exists nothing over here on the other side. So within this the particle is acting as a free particle. So particle within this region or the potential is the completely free. Okay, and except at the two ends, so, and the boundary we are on defined it. Okay, so here an infinite force actually prevents the particle from escaping out of it. So classical model would be a cart on a frictionless horizontal air track with a perfectly elastic bumper. It just keeps the bouncing back and the force. So this is something like a object which is trapped within a certain region and it wouldn't be able to move out of it. Okay, so this is something like the frictionless car just going on the track, having the perfectly elastic bumper. So this potential is awful artificial, but I urge here to you to treat it with respect. Okay, despite its simplicity, or rather we can consider precisely because of its simplicity, it serves a wonderfully accessible test case for the all the fancy stuff that comes later. So we'll refer back it to it very frequently. We'll be coming back to this problem again. So it can give us the very much important base for the solving the various problems in the future. So outside the well, what happens that the potential is infinite, so the wave function doesn't exist over there. Wave function doesn't exist, so wave function is 0. The probability of the finding particle there is 0, so wave function itself is a 0. So wherever the potential goes to the infinity, the wave function has to vanishes there. Okay, and now we'll talk about the inside the well what is happening. So the inside the well, here the potential energy is 0, so the time independent Schrodinger equation reads to be like this. Okay, what it is, that is minus h cross square by 2m d2 psi by dx square is equal to e psi, because this is we are just talking about the one dimensional case only. Okay, so that's why we have just defined the d2 psi by dx square, or else we can just rearrange the equation in such a way that d2 psi by dx square is equal to minus twice ma by h cross square psi, and I define here as the k square is twice me by h cross square as a constant one, because total energy of the system is constant and the other mass and the h cross reduced Planck constant is again a constant. So I define this here, the k square as twice me by h cross square. So it has tacitly assumed that the E is always greater than or equal to 0. This is total energy which is greater than 0, equal to 0. We know that if a total energy is less than 0, it doesn't work for the in this case. So now let's try to understand the equation is the simple harmonic equation over here. So this equation seems to be the simple harmonic equation. Okay, the general solution corresponding to this is this equation is something like a second order differential equation. So we'll be having the two constants again here, and here do remember that whenever the particle is trapped within a certain range, then obviously we'll write down our it's a solution of the such a differential equation in terms of the sine and cos. Okay, and whenever the particle is going coming from the infinity and just interacting and going towards the again plus infinity, then in that case we will try to write down its solution in terms of the exponential e raised to ikx and b into e raised to minus ikx kind of the solution will be having when the particle is coming from the infinity and going towards the infinity. Then we will write such a solution to that differential equation. Here the a and b are the some arbitrary constants and which are fixed by the boundary conditions of the given problem. So what are the appropriate boundary conditions for the psi of x? Actually, what are the appropriate boundary conditions for the psi of x? In general, what we used to have ordinarily, both psi and d psi by dx are the continuous, but here the potential goes to the infinity, only the first of the these applies. Okay, so whenever the potential goes to the infinity, then the second doesn't work, because that is comes under the infinite discontinuity over there. So we need to deal with in the other way around. So only the first boundary condition only survives here. So let's talk about the continuity of this boundary conditions here, or the continuity of this equation. So that is, continuity of the psi requires that the on the psi of x is equal to 0 has to be equal to psi of a is equal to psi of x is equal to a, which has to vanish on the end of the, or the boundary of the potential well. Okay, so as to join onto the solution outside the well, what we can have, just psi of x is equal to 0. So we will try to substitute the value of the first boundary condition, that is psi of x is equal to 0 is equal to a sine of 0 plus b cos 0. So what happens, that sine 0 itself is 0, so it doesn't matter that what is the value of the a. So this will result us into the b cos 0. Cos 0 is 1, so it remains only the b. So psi of x is equal to a, which is vanishing one. So what happens here, the psi of x is equal to 0 is 0, which is equal to b. So this will result us into the b is equal to 0. So we'll try to substitute this b is equal to 0 in the our total wave function. So our wave function becomes the psi is equal to a sine kx. Then try to substitute the value of the another boundary condition, that is psi of x is equal to a sine ka. Now here there are two conditions to have vanish this potential, wave function has to 0, because this is the infinite discontinuity at this x is equal to a. So x is equal psi becomes 0 on the left hand side, so a sine ka. So here there are two possibilities, either a has to 0 or the sine ka has to 0, or it has to vanish. If suppose we take the a is equal to 0, then total wave function becomes a 0. Okay, so if a becomes a 0, then there becomes a total wave function becomes a 0, in which case we are left with just a trivial non-normalizable solution psi of x, because we are just dealing with the nothing. So what we can have, we will choose the sine k as equal to 0, which means that the k is equal to 0 or plus minus pi, because whenever the sine goes to 0, whenever the sine or that angle is multiple of the 0 or pi, okay, 0 or the pi, if it is multiple of the pi, so 0 plus minus pi plus minus 2 pi, so and so forth. So that vanishes. So sin theta vanishes at this point. But if suppose k is equal to 0, again is not a good solution, and negative solution does not give anything new. So what we can have, sine of minus theta is equal to minus sin theta. This negative sign can be absorbed in our constant, which is carrying along with sin k. So that is not the big deal to absorb that sign. So the distinct solution will be the kn is equal to, n stands for that one particular state, so kn is equal to n pi by a with n is equal to 1 2 3. So curiously, the boundary conditions at x is equal to 0 does not determine the constant a, but rather the constant k. Hence the possible value of the energy means what, here we got it, we got the energy corresponding to it, because k is related to the energy, not the wave function one. So we can just try to calculate the possible value of the energy corresponding to it. So En is equal to h cross square upon 2m kn square, as we can go back to the our earlier equation as equation number here. Okay, defined the, not equation number, but the constant which we have defined earlier one. So this equation can be represented as equation number 8. So this is the energy corresponding to that particular nth state. So in a sharp contrast to the classical case, the quantum particle in infinite square well cannot have just the any old energy, okay, but only these special allowed values only are there, okay. So the wherever the n is just the integer values 1 2 3 4, okay. So well, how do we fix then the constant a? How to fix the constant a? And answer, normalize the psi. So let's try to normalize the wave function corresponding to it. What is the normalization condition for the psi? Integration from minus infinity to plus infinity, psi star psi dx is equal to 1, but we have given the interval as a 0 to a. So we can just integrate between the 0 to a, because particularly just exists between that only. So 0 to a region of the that plus minus infinity region is we have considered here. Psi star psi dx is equal to a. What is our wave function here? That is nothing but the psi of x, a sin kx. Just a, we don't know the whether a is a real or the imaginary one, so we can just consider that as a star sin kx into a sin kx dx is equal to a. So mod a square, a into a star becomes mod a square into is independent of integration, integration 0 to a sin square kx dx is equal to 1. So but what is the value of the sin square kx? That is nothing but the a by 2, because region is given as a 0 to a. So what we will get it? Mod a square is equal to a by 2. Now mod a square is equal to 2 by a. This only determines the magnitude of the a, but it is simplest to pick the positive real root of it. So we have just considered the positive real root of it. So a is equal to root 2 by a. So inside the well, the solutions are something like psi n of x root 2 by a sin n pi by a into x. K is nothing but the n pi by a. So the time independent Schrodinger equation has delivered an infinite set of the solution, only one for the each integer value n. So few are just I'm going to plot in the here. That is nothing but the first wave function here within this region is something like x is equal to 0 and x is equal to a. So what happens that if suppose n is equal to 1, if I consider, then root 2 by is a constant one. So sin n is equal to 1 pi by a x. So what happens that the only half part of the wave function is just considering here, it vanishes here, because at the boundary it gets vanishes. X is equal to a and x is equal to 0 and x is equal to a, again the becomes a sin pi is 0. So it follows only the half curve of it is. So this is something like the psi 1, okay. Now I am going to plot the another wave function, that is psi 2. Then what is the solution corresponding to it is that is nothing but the okay. So this is v. So psi 2 of the x. So we are plotting for the n is equal to 2. So what is the plot here? Sin 2 pi x by a. So when x is equal to a, then sin becomes 2 pi. So this total interval is a 2 pi. So what we can have, the integration becomes like this, okay. So this is the psi 2 of the x. So if I just plot the n is equal to 3, then our graph becomes something like, okay. So I should have been plotted over here, the n is equal to 1, n is equal to 2, 1 2 here, n is equal to 3. So what happens that there is the something like this equation it corresponds to, because it becomes a. So these are the something equations are the plots corresponding to the various n values, okay. So three stationary states of the infinite square wave potential are plotted over here, okay. Now let's try to understand that the various properties of the this wave function. So here the psi 1 here which carries the lowest energy is called as the ground state one. So psi 1 which carries this lowest energy is called as the ground state. The other whose energies increase in proportion to the n square are called as the excited states. So a group of the functions psi n of x has some important and interesting properties. We'll try to see over here, that is they are alternatively even and odd with respect to the center of the wall. If we just try to consider the center of the wall, then we can consider here that alternatively it will be this is a even function, this is a odd function over here, this is again even, then next will be the odd one. Okay, so here psi 1 is even, psi 2 becomes odd, psi 3 becomes even, and so on, this cycle goes on, right? As we go up in the energy, each successive state has the one more node. Okay, so nodal point here, nodal point is nothing but where the wave function goes to the 0. So at this point, the nodal function has a one node. Here we can have the two nodes here, okay, 1 and 2. Apart from the what you can say, the boundaries, okay, apart from these boundaries we will be having the another node called in between. So because we know that at the boundaries it has to vanish its wave function because of the infinite potential. As we go up in the energy, each successive state has the one more node. Okay, so the third one is nothing but the they are mutually orthogonal to it. Mutually orthogonal in the sense that the condition of the orthogonality in case of the wave function is a psi m star of x into psi n star of x dx is equal to 0, provided that m is not equal to the n. Okay, if they are not corresponding to the same state, it gets vanishes. Okay, and this is also represented with the Kronecker delta function. So we can represent the psi m star of x into psi n star of x dx is equal to delta mn. Delta mn is a Kronecker delta, and its value can be how the delta mn becomes a 1 if m is equal to n and is equal to 0. Sorry, if delta mn is equal to 1 if m is equal to n, and delta mn becomes a 0 if m is not equal to n, and they are having the complete set of the solutions. So the wave function has complete sets in the sense that the other functions f of x can be expressed as a linear combination of the them, that is nothing but the f of x is can be represented with the n is equal to 1 to infinity cn psi n of x. Okay, so this can be represented in the sense that the psi n can be given with this original wave function here. So we will try to talk about this on the next lecture as well. So they are how they are becomes a complete one, okay, or how to find out the cn value. Thank you.